Hello, everyone. Good afternoon. Welcome to the distinguished lecture series hosted by the Faculty of Science at the University of Hong Kong. My name is Shuang Zhang. I'm a professor in the physics department and associate dean of the Faculty of Science. So it is a great pleasure to chair this session today. For those of you who don't know, the distinguished lecture series are hosted by the Faculty of Science, and it features the talks by world-leading scientists. Okay. In their respective fields, covering a broad spectrum of topics from math, physics, chemistry, material science, and biology, and this interdisciplinary field as well. So this is the first lecture of this year, and we are very pleased to have a renowned scientist, Professor Nigel Brandon from Imperial College London, to give a talk on electrochemical technologies. Now, I would like to pass on to the Dean of the Faculty of Science, Professor Vivian Yan, to introduce our speaker. Yeah, Vivian, please.
Yeah, thank you, Xiang. So, colleagues, students, guests, welcome to this Faculty of Science Distinguished Lecture entitled Innovation in Electrochemical Technologies for the Low Carbon Energy Transition. So I'm Vivian Yan, the Dean of Science at HKU. So technologies that could flexibly and efficiently make use of electrons for sustainable energy conversion and vice versa will be of increasing importance as the world moves to net zero carbon economies. As such, electrochemical technologies such as electrolysers, fuel cells, batteries will play a very important role as it already become evident. But there remains still a need to lower the cost of these technologies, maximizing their efficiency and increasing their lifetime. And hence innovation remains an important focus. The talk of Professor Nigel Brandon will draw on his experience in founding 2 companies from his academic work. And Professor Brandon will discuss the challenges and opportunities for further innovation in electrochemical technologies and highlight some of his group's recent work in high temperature electrolysis for very high efficiency electrolysis as another area with great potential. Now, it's my great pleasure to introduce our speaker, Professor Nigel Brandon, today. Professor Nigel Brandon is the Dean of Faculty of Engineering at Imperial College London. And in fact, I'm really happy to learn that he has just been elected to international member of National Academy of Engineering for his contributions to the science and engineering of solid oxide fuel cells and to their technological development and commercialization. He received an Order of the British Empire, the OBE, in 2011 for his services to UK-China science in the field of energy and climate change. And in fact, I've known Professor Brandon for quite some time because we served together as serial editors of the Royal Society of Chemistry, Energy and Environment book series. And we have regular meetings then. Professor Brandon's research focuses on electrochemical devices for low carbon energy applications with a particular focus on fuel cells, electrolyzers and batteries. He is the director of the UK Hydrogen and Fuel Cells, Supergen Hub, and chair of Imperial's Sustainable Gas Institute. He's the founder of Ceres Power, an AIM listed fuel cell company spun out from Imperial College in 2000, and the founder and director of RFC Power, a flow battery company spun out from Imperial College in 2018. So he has been extremely successful. And as I was telling him that the Hong Kong government is really now investing a lot of money looking for entrepreneurship, training our students to have spin-off companies and so on. So it would be extremely our great pleasure and honor to have Professor Brandon to be here to give the talk. And he's also a partner in Galvanic Energy, which offers specialist consultancy services in the electrochemical technology space. Now, without further ado, I will now pass the floor back to Professor Brandon to deliver his distinguished lecture. So Nigel, please, could you share your screen?
Yeah, thanks very much, Vivian. Can you now see my screen?
Yeah, it's perfect. Yeah, thanks.
Okay, let's just check this with this now. Let's just check it moves. Yes, it does. Okay. Well, look, it's a pleasure to be here. virtually. As I said to colleagues in the conversation ahead of this, it would be even more of a pleasure to be with you in person. And so hopefully at some point we can manage that. And thank you for the very kind introduction. Yes, I want to talk about innovation in particular, and in electrochemical technology for the low carbon transition in that context. It's interesting to learn the focus on entrepreneurship and innovation that is emerging or in place in Hong Kong. It's an area I'm particularly passionate about, and understanding how you take your science and your engineering science into application. And I'm very happy to take questions on that. I'll give a couple of examples drawn from my both the companies that I'm involved in, which are at different stages of maturity through my talk. So I want to kick off by saying why am I talking to you about electrochemical technologies, and why do I think they have a role to play in the low carbon energy system? It's very evident now that batteries, for example, for electric cars are of growing interest. But these have been areas that people have been working on for 20, 30, 40 years. And I think we have to remember that sometimes these technologies take 20 or 30 years to come through. So we do need to look ahead. We always need to look ahead as to the future needs, as well as the current technology challenges. I'm going to focus in terms of the talk today on 3 types of technology. I'm going to talk about fuel cells, and specifically really solid oxide fuel cells, which is what I've spent a lot of time working on. I'm going to talk about electrolyzers, and specifically high temperature electrolyzers. And I'm going to talk about flow batteries, and specifically a liquid gas hybrid flow battery that we are trying to commercialize. And then we can obviously very open to questions on any of these topics. For each of these topics could be the subject of a 1-hour talk easily. I'm going to then give an overview really of how I see the field of green hydrogen, which has become extremely topical in the last few years, finally. Where hydrogen fuel cells for transport fit, where fuel cell combined heat and power fits, where energy storage for system balancing. I'm not going to talk about batteries for electric cars. That's another important topic, but it warrants its own focus. And the role of hydrogen in industrial decarbonisation. So we're going to try and do all of that in 40 minutes. So we'll see how we get on, and then please do ask questions afterwards. So why? So the context is, of course, specific to the region. This is the UK, and of course, it will be different in different parts of the world. It'll be different in Hong Kong. But this is a flow. This is a figure comes from the University of Birmingham. Now we are in the University of Birmingham. That's the mention of the University of Birmingham we were talking about earlier. Yes, so Grant Wilson at the University of Birmingham produces this data. It's a very good synthesis for people to use like myself. And it shows the energy flowing through the UK energy system. And this is in gigawatt hours on the vertical axis and time. And it shows the energy flowing in the red line as electricity, in this line as gasoline and diesel, so liquid fossil fuels. This is the pandemic hitting and the fall off in transport fuel demand, some fall off in electrical demand. But interestingly, this line here, which is the demand for natural gas, so this is energy flowing as natural gas, was barely impacted by the pandemic. And that's because most of this is for heat, and it's therefore quite a difficult thing to displace. And you can see the challenges in decarbonisation. This line is relatively easy to decarbonise. I say that, the word relative cautiously, but we have renewable technologies that can decarbonise that line. We could then use that electricity to help decarbonise this line, which is the liquid fossil fuels, gasoline and diesel. But you can see we need an awful lot of electricity, additional electricity to do that. Now, of course, an electric car is more efficient than an internal combustion engine car. So it's not like for like, and the efficiency may well be, 2 or 3, even 3 times as high. But nonetheless, we need significant capacity to achieve that. And then if we want to displace natural gas, which we also can't continue to use in unabated form in a net zero economy, we either have to have carbon capture or we have to use a different energy carrier. If we want to convert all of that heat that comes from natural gas from electricity, even with a heat pump, with a coefficient of performance of say 3, you can see that our peak heat demand here is up at about 3,300 gigawatt hours. And if that coefficient of performance was 3, we'd need 1,100 gigawatt hours of electricity, which of course would double the entire generating capacity of the UK energy system. And that's possible, but it becomes very expensive. So the question is, can hydrogen or be a low carbon molecule that could replace natural gas? So that's the kind of context for the transition that we're dealing with, at least in a UK context. So electrochemical technologies feature there because we might think about using hydrogen as a carrier. We might think about how we make that hydrogen, and electrochemical processes are one important potential component of that. We might think about how we convert between electrons and molecules and between molecules and electrons as being an important set of technologies in that transition. Of course, electrochemistry sits at the heart of those conversion processes. Talking there about carbon, we shouldn't forget that it's not only about carbon, it's also about air quality. This is a NOx map. It's a bit old now, but I don't think London's got any better of the NOx emissions in London. And the red line is the high NOx emissions. And you can see those NOx emissions are associated with the main arterial road system in London. And this is Heathrow Airport at a time when people still used to use aeroplanes. So they obviously that emission is will go back up again as the pandemic eases. So hydrogen is one of the important components here that will run through my talk, either making hydrogen or using hydrogen. And just to sort of be very clear, hydrogen has different, can be produced by different means. If we make hydrogen today, we tend to make it from fossil fuels like natural gas. And we do this without, we make it from fossil fuels like natural gas. And we do this without carbon abatement, and that creates CO2 emissions. If we make our hydrogen from fossil fuels with carbon capture, we refer to that as blue hydrogen. It's a low carbon hydrogen. And if we make it from renewable power by electrolysis, we refer to it as green hydrogen. And if anyone's interested in this and doesn't work in it, I commend you to this report that I helped produce, but it was produced by a team through the Royal Society in the UK, Options for Producing Low Carbon Hydrogen at Scale. And I think that it makes the point that you can make hydrogen via various different routes: biological, electrolytic, thermochemical, with or without carbon capture. And they can take you from different energy carriers through to hydrogen. And indeed, if we go with a biomass feedstock and come through carbon capture route, we can even produce negative emission hydrogen that uses more carbon in its production than the energy it produces. So that's the advantage. I mean, the disadvantage, of course, is that all of these conversion steps add cost, and all of these conversion steps carry an efficiency penalty. So the other thing I should say is if we can use renewable electrons directly, then we should do so. But if we can't use renewable electrons directly, either because the battery technology is not sufficient for the application, or because those electrons are produced in a location where we can't use them, then that's when we might want to consider converting them to an alternative energy carrier like hydrogen. Okay, so this is another cartoon of the same picture, which came from a paper we wrote some years ago, a review paper. And again, it shows the interconnectivity between primary energy sources, wind, solar, or nuclear, for example, at the production of electrons, and those conversions of those electrons into chemical carriers like hydrogen, or indeed the combination of that hydrogen with CO2 in a methanation reaction to give us a methane, which we might then choose to use, so a synthetic methane. Okay, so that's the context, and I hope what you've picked from that is that electrochemical technology has an important role to play in many of those conversion processes. So let's talk about electrolysis next. A topic that's emerged is of increasing interest in the last few years. Now, there are various ways you can put electricity into water to split that water and make hydrogen and oxygen. Alkaline electrolyzers have been with us a long time. They're over 100 years old. They're a mature technology. You can buy 100 megawatt electrolyzers and run them. and there are companies that sell that. As a consequence, this is the cheapest electrolyzer available today. But they were never really built for integration into renewable systems. They really are base load electrolyzer. They occupy quite a lot of space. Their power density is relatively low. Their efficiency is about 65% or so. But they are, as I say, the most mature and most have the best kind of global supply chain today. And a number of the world's large electrolyzer programs utilize alkaline electrolysis. But they're not very good at load following. They're not very flexible, and they don't produce hydrogen easily at pressure. PEM electrolyzers are relatively speaking a newer technology, though they are now commercially available at scale, at the kind of megawatt scale and above. They have the advantage, they're sort of derived to some extent from PEM fuel cell technology. They have the advantage of being more flexible. They have the advantage of producing hydrogen at pressure, which is good for things like vehicle refueling. But they do contain iridium and platinum, and indeed titanium, and have expensive membranes. So I think there is still remains an open question in my mind about the scalability, the really global scalability of this technology until we've addressed some of these supply chain issues. So there are interesting catalysis questions around PEM electrolyzers that I'm sure colleagues in your university are knowing some of them, like Xiao Go, Professor Go, are well placed to address. And then the area I particularly work on is solid oxide electrolyzers. Talk about that more in a moment. This is a more nascent technology, certainly not commercially mature. There is a company in Germany that will sell you an electrolyzer, but plenty of work to be done to bring this technology through to scale. But it has the advantage of being much more efficient than these low temperature types, and I'll show that next. So what about cost? And it is the case today that green hydrogen made by electrolysis is far more expensive than hydrogen made by any other means. 60 to 80% of the cost of that hydrogen is the cost of the renewable power that goes into it. So there's a very strong coupling between renewable power costs and green hydrogen costs. This is some work from IRENA, the International Renewable Energy Agency, and it's a useful report. It's quite a positive report. I guess I would say it's a sort of rose-tinted view of the future cost down potential for hydrogen, but nonetheless it paints a picture of a route down to $1 a kilogram hydrogen. But you will see other commentators who feel that this sort of price point is achievable. It's sensitive to some extent to the reduction of cost of the electrolyzer, but also sensitive to the renewable energy price. And that's why you're seeing green hydrogen projects today at scale being developed in parts of the world which are advantaged in terms of their renewable energy price, like Saudi, like Australia, where they have low-cost renewable electrons available. So we can see a path down towards low-cost green hydrogen, provided renewable power costs continue to fall as the technology is deployed at scale, and provided the electrolyzer costs continue to fall as they are manufactured at scale. And I'm confident that both of those things can occur, but of course, that's still got to be delivered. Now, I mentioned high temperature electrolysis. It's an area I'm particularly interested in. And the reason is kind of painted a picture on this thermodynamic plot, which plots a temperature here against energy requirement, and it shows the enthalpy and the Gibbs free energy for water splitting. As we go from liquid water to steam, we obviously get the latent heat of vaporization of water. And so if we're putting in low-grade steam, we can see that it will require less energy just because you haven't got to go through this latent heat of vaporization of water step. But also, as we as we move to higher and higher temperatures, the Gibbs energy here, which really defines the electrical energy demand, goes down, whilst the total energy demand, of course, is constant. It means that we can put in less electricity and more heat, if that's what we wish to do so, to split water. So it provides us the opportunity for reducing the electrical energy demand and providing some of that energy from heat, and generally heat is less valuable than electrons. So for things, for example, where you may be integrating in with other industrial processes, where there's low-grade steam around and perhaps some heat around, we can think about very high efficiency processes. And this can be translated into the graph at the bottom, where we can see that in an electrolyzer, which is this side of this plot, firstly to say that for a high temperature device is completely reversible. We haven't got to go through a liquid phase transition, liquid gas phase transition. So it's a completely reversible electrochemistry. But in electrolyzer mode, we can either operate endothermically down here, in which if we have additional heat available, we can recuperate that heat into the energy content of the hydrogen we produce. Or we can operate at thermoneutral voltage, so-called, at which the net heat generated in the reactor is 0, and so we get a very flat temperature profile. Or we can generate in exothermic mode, in which we are producing the heat we need to drive this reaction from irreversible losses in the electrolyzer. This will lower the efficiency, but it may be a mode we choose to operate in. This all translates into a plot like this, which comes from this useful review paper from a few years ago now, which paints a picture of the different electrolyzer technologies with PEM electrolyzers, solid oxide electrolyzers, and alkaline electrolyzers. And I certainly don't want to argue that we don't need different types of electrolyzers. I think we do. And I do think there's a very strong role for PEM electrolyzers, provided we can assure ourselves as the supply chain of the catalysts. But you can see that with solid oxide electrolyzers, we can get very high efficiency. And indeed, if we start to operate in endothermic mode and recuperate heat, the electrical efficiency goes over 100%. Of course, that's not the actual efficiency because we're still putting energy in as heat, but we're recuperating some of that into the calorific output of the hydrogen, giving an apparent electrical efficiency of over 100. But nonetheless, the electrical efficiency is always high. And even in thermoneutral mode here, you're approaching around 96% electrical efficiency, which is clearly attractive in a technology where 60 to 80% of the cost is in the cost of the power. So that's why I and others are interested in high temperature electrolysis. What do we do on high temperature electrolysis? Just to paint you a picture in case you're interested in any of the science that we undertake in this space. My group is particularly interested in the materials engineering and particularly the engineering of electrodes. And one of the challenges you find in high temperature electrolysis is that the conventional materials that are used today, which contain a lot of nickel, are subject to sintering. The nickel in the high steam content of an electrolyzer, the nickel tends to agglomerate and sinter. And so we're trying to explore routes by which that nickel sintering doesn't occur. One way we're doing this is using electrospinning to produce fiber networks and then infiltrating those fiber networks with oxide ion conducting materials. We have to produce porous composite materials for these electrodes. And so this is the type of thing we're exploring. And I have a very talented postdoc that's working on this. And he's done some really interesting work around the creation of these fiber structures. And we use techniques like 3D imaging to resolve the microstructural orientation and to understand the nature of these interfaces. And the work is encouraging. And we're continuing to take that forward. We will see whether it proves of sufficient technological value. The other approach we've got, and Xiao, you might remember this from your previous life at UCL in London, where we collaborated, in fact, initially with colleagues at UCL to look at these nano composite materials. And this is also interesting, where we appear to be able to get more stable high surface area nanocomposite materials, which in which the stability, and this is by no means long enough technologically, but it's not, if this was a non-nano, if these materials were not incorporated in this way, their degradation would take a matter of an hour or two. So we've got some 60 odd hours of fairly stable and high performance, and we want to continue to pursue this approach. So we're not, I think it's fair to say we're still working through exactly how this works, but it's encouraging. So innovations like this to get lifetime, and the critical barrier here is lifetime, are an area of opportunity for innovation. I'm happy to discuss more in Q&A. Okay, so let's move on, conscious of time, and just look at hydrogen fuel cells for transport. So we're talking about fuel cells now. We're talking not about putting electricity in and splitting water. We're talking about putting hydrogen and air oxygen in and making electricity. So it's the reverse reaction. There are two broad classes of fuel cell technology: low temperature PEM fuel cells. These are the type of fuel cells when we look at cars and transport applications, what one commonly sees, using a proton conducting membrane that is proton conducting when hydrated, and with catalytic, with precious metal catalytic electrodes on the anode and cathode. I'm also going to talk about solid oxide fuel cells, an area I've spent a lot of my own time working on. Same principles, we put in fuel and air, oxygen from air, we produce power, but now we have an oxide ion conducting membrane. And these are ceramic materials which are able to conduct oxide ions at elevated temperatures of somewhere in the order of 600 to 800 to 900 degrees centigrade. Okay, so on the PEM side, the challenges are all about water management primarily, and catalysis, and to some extent membrane stability. On the high temperature side, the electrochemistry is very facile as a rule because of the temperature, but we are concerned about things like thermomechanical properties and structural integrity and long-term degradation of materials at temperature, at interfaces and sintering and so on. So the problems are quite different in the two devices. But for those who don't follow this field, this is to some extent, if you like, the poster child of hydrogen fuel cells for a long time, which is fuel cell electric cars. This is the Toyota Mirai that we have at Imperial. And of course, there are big programs around this in different parts of the world, particularly in Japan and Germany and the US. The rise of battery electric, I think, is really taking over from hydrogen fuel cell electric light transport at the moment. That's not to say that light transport doesn't have a role, but I don't think it's the first place I expect to see mass rollout of hydrogen fuel cell transport. But nonetheless, it could become important in the longer term. I do think that areas like this, which is these are hydrogen fuel cell electric buses, I do think those are of great interest. I have to say I haven't looked to see what's happening in Hong Kong, but certainly there's a lot happening elsewhere in your part of the world, in Asia, around hydrogen fuel cell electric buses. And I think the public good agenda here, the fact that these are fleet vehicles operating from a fixed site at which the hydrogen infrastructure is easy to deploy, and where local air quality matters, gives this a really interesting opportunity. This bus here, it says on this slide, was developed by Arcola Energy, who are a small British company who've just actually been purchased by Ballard. So that's an interesting development here in the UK. A relatively new area, which is also looking really interesting, is hydrogen fuel cell electric trains. These are to replace diesel electrics on those aspects of train lines which don't warrant the capital cost of electrification. Some of these are now being trialed. They've been run in Germany and Austria for some time to good effect, and we now have some on trial in the UK. So another interesting transport opportunity. And then I do think that this is a really important opportunity, which is around trucks and larger vehicles, which are going to be difficult to electrify using batteries. That's not to say it can't be done. And of course, there are companies working hard to develop battery electric trucks and larger vehicles. But certainly the energy requirement of that vehicle makes a battery-only solution a more challenging thing to do. So this is from JCB, a British manufacturer of off-road construction vehicles, and this is from Hyundai, hydrogen fuel cell truck in Switzerland. So for me, this is this, along with the bus market, is an interesting adopter. I haven't got any slides on it, but I also think that hydrogen for aspects of marine or green ammonia, which you make from green hydrogen for long distance shipping, and also hydrogen for aircraft, particularly more regional aircraft, are also of great interest. Okay, so let's move off transport and move on to stationary heat and power, and the role of fuel cells as a high efficiency energy conversion device for heat and power. Now I show this slide because this is talks about gas networks, and when we start to think about fuel cells for heat and power, we need to think about where we get the fuel from, and of course that's going to come from gas. Today, that is largely, in most parts of the world, natural gas. This plot here shows how sensitive different countries are to the utilization of natural gas for heat. And this is the Netherlands, and the UK are second and Italy are third. So the UK has the second highest reliance on natural gas for its residential heating. Anyone who's spent some time in the UK will probably recognize the fact they had a natural gas boiler in their home. And it makes, therefore, for us and for countries that have become reliant on, in our case, this case here, North Sea gas for heating, a really difficult transition away from that to a low carbon equivalent, because natural gas, unabated natural gas, you clearly can't use in a net zero energy system. So we've done quite a bit of work on this, as have others. This is from Japan. It's the well-known Enifarm program in Japan, which looks at a vision of a low carbon home in Japan with renewables, with local energy storage from a battery, but also with a fuel cell, producing additional supplementary heat and power. In this particular case, that's still fed on natural gas, because that's what was available. But you can switch out natural gas into hydrogen, and actually all fuel cells like to run on hydrogen. It's easier than running on natural gas. So that is something that can be readily done. Now, I'm interested in solid oxide fuel cells. So that's the higher temperature fuel cell type I mentioned earlier with the ceramic electrolytes. And just again, for those of you who don't follow this field, there are, broadly speaking, three different types of technological solution for solid oxide fuel cells. The top figure here shows what we call an anode supported design, in which the mechanical component is this relatively thick anode. That's a porous composite of a metal, usually nearly always nickel, and an oxide ion conductor like yttrium stabilized zirconia or gadolinium doped ceria, on top of which is a thin, sort of 10 micron or so thick, a dense electrolyte, and on top of that is a thin cathode material, which is often something like a lanthanum cobaltite or lanthanum ferrite or lanthanum strontium manganite. Different materials are used for different temperatures. And the challenge in all of these materials is, how do you ensure a gas-tight electrolyte that doesn't fracture in service? And how do you layer these cells up into stacks and ensure gas-tight seals between the cells without inducing strain as the materials expand and contract on heating and cooling that creates fracture of these delicate ceramic components? Effectively, this is a thermomechanical technology as much as it's an electrochemical technology. This type of technology is pursued by companies like Fuel Cell Energy in Canada, by Solid Power in Italy, and companies like that. The other approach is to have what we call a self-supported electrolyte. So the electrolyte's about 150 microns or so thick. It's the ceramic, so it's typically an yttrium stabilized or scandium stabilized zirconia. At that thickness, is like a thin sheet of paper, but it's strong enough to support itself. It doesn't need an additional mechanical element to provide that support of the ceramic layer. And on top of that is, on the underside is a thin anode, and on the top is a thin cathode. And these are fine, but for reasons you need with a thick electrolyte, you have a longer resistive path, because the oxide ion conductivity is the lowest conductivity of any of those materials. And obviously with a thicker electrolyte, we have a higher internal resistance, and therefore a lower power density or a lower efficiency, and hence a cost implication. And also the ceramic is quite expensive, so use more of it. The third approach, and this is the approach we pioneered in our work at Imperial College, and that led to the spin-out company Ceres Power that was been mentioned in the introduction, was to replace these ceramic components with a metallic component, and to have the structural component as a porous ferritic stainless steel, appropriately protected from the chemical environment with a coating. And on top of that, three thin layers: the anode, the electrolyte, and the cathode. And that was a very different approach. It allows you to use welded joints, because you have metals in contact with metals rather than trying to have delicate glass ceramic seals. And typically, and in the case of Ceres, a lower operating temperature of 500 to 600 C, enabled by the choice of a different electrolyte material, gadolinium doped ceria, rather than yttrium stabilized zirconia, that lowers the temperature and allows gasket seals again, which help with the engineering of the seal. So this is just from the literature, if you like. This is a classic anode supported cell. You can see here the electrolyte about 10 microns thick on porous electrode materials. This is a typical electrolyte supported cell. You can see here the much thicker electrolyte, 120 or so, 130 odd microns thick, again with the porous electrode materials. And then this is the metal supported cell that came out of our work at Imperial College, based on a research grant from the UK Science Agency in 1998 that led us to file this patent in 2000. And this shows you the concept, which is this porous metal support with the 3 layers on it. And this is a photograph of a copy of that core patent that underpinned the company that we translated it into, which is Ceres Power. So this is the cell today that Ceres make. This is what an actual metal supported solid oxide fuel cell looks like. You can see that the metal plate here has got various channels cut into it, which are for manifolding purposes. You can't see the anode is actually this very slight layer that you can see in silver here, and on top of that is this reflective surface. That's the 10 micron thick electrolyte. This cell doesn't have the cathode on. If it had the cathode on, it would just look like a layer of black paint. On the top, you can see the sort of prototyping line here, and this is a stack of cells which would generate you a kilowatt or so of power. And there's a video on this website, which is a popular YouTube website for looking at low carbon technology. This is based on public information that the company issue, and in fact, underlying that is quite a lot of material science. The ferritic steel, nickel Ceres cermet anode, gadolinium doped ceria. Actually, that electrolyte in itself is more complex. It actually contains an electron blocking layer, and that matters because gadolinium doped ceria can become a mixed conductor at temperature in a reducing environment. And so an electron blocking layer is incorporated to prevent electrical short circuits across the electrolyte. So you can see quite a lot of complex material science evolved into this process, but all done with low-cost processing like screen printing and so on. The seal itself, you can see, has, and this is a critical element of the technology, is you have these ability to have these welded connections to give you a gas-tight seal, which is stable to thermal expansion. So where is the technology today? Well, the technology we set up, as I say, back in 2000. The company value today is just over £1 billion on the stock market. It's got about 500 people. It's got a factory in Germany and a factory in the UK. It's got commercial partnerships with these organizations here. Recently, the company has expanded its remit not just into power, but also into hydrogen as an electrolyzer variant, and they're developing a 1 megawatt electrolyzer at the moment. And you can see there you can buy a unit in Japan with a Ceres stack inside it. It's a 4.2 kilowatt unit. Bosch in Germany are developing this into a range of products and there's also a product with Doosan in Korea, and Weichai are putting this technology into buses in China. And this just shows you a little bit more detail of the Doosan, Bosch and Miura programs. So it's a 20-year journey to get to that point. I'm happy to take any questions on what it's like to take your research through that journey, and it's had its ups and downs for sure. But nonetheless, great to see the interest in the technology and seeing it finally come through after all those years. For those who perhaps don't follow the fuel cell sector, I will always commend you to look at this review if you want to find out what's happening globally. It's free and available from E4Tech, who produce it. And it paints a picture of where things are commercially. The most recent review came out in 2020, came out in 2021, and shows here the distribution of fuel cell sales. So these are shipped units in numbers of units. And so this is in thousands, so just over 80,000 units shipped globally. forecast in 2020, dominated by PEM. So that's the transport market. But you can see solid oxide also on the radar there. And if we go to megawatts, you can see that we're now, this is now into, finally, gigawatt scale sales of fuel cells globally, again, dominated by PEM for the transport sector with solid carbon, with some phosphoric acid, which is still around, but a bit of a legacy technology, and solid oxide here. Okay. I want to move on in the last 5 minutes to a couple of other areas. I want to talk about energy storage first for system balancing. And this just paints a picture of some of the challenges of putting more and more intermittent renewables into the energy system. This comes from my colleague Goran Strabak at Imperial, who's a power system economist. And effectively, the picture is that as we put more and more renewables into the system, you might remember from that opening slide that if we're going to replace, for example, all of our natural gas with electricity, we end up with the need to double our electrical generating capacity, but we only need it in the winter. That means we're going to put in a lot of capacity and a lot of transmission lines and but we're still going to move the same amount of it. We're not going to move a lot more energy, but we're going to need a lot more capacity. So the utilization of those assets goes down over time, which means that we're not benefiting from that capital investment. Alternatively, and in addition, we also have to find a way of as we put more and more wind into the system, and this is a wind example because that's relevant for the UK context. As we put more and more wind into the system, we have to find ways of managing that peak wind generation, often occurring at times when we don't need it. And that can lead to significant curtailment of wind generation. So again, you're not utilizing your capital investment. So the question is, what role can storage and technologies like that play that offset this degradation in capital utilization? In other words, rising costs. So that's one case. This is a case from California. Looking at the penetration of solar PV in California, which is forecast to be a rather, very large penetration. And of course, you get this requirement for diurnal cycling, where the solar is generated in the daytime, but not generated in the nighttime. And certainly the forecast there is that in California alone, they need around 44 to 55 gigawatts of energy storage, and that storage needs to give you about 10 hours of storage. And 10 hours is tricky to do with a lithium-ion battery, can be done, but it starts to get expensive as the energy storage duration goes up. So bearing in mind all of that, we've been working with another new technology that we're trying to take forward at the moment. It's a much more nascent technology than the Ceres technology now. We set this company up in 2018, but it's based on a number of years research prior to that. And the concept here is to move away, is firstly to use a flow battery. And the idea of a flow battery is that you can produce your energy storage as a redox couple, normally a liquid, that you store in a tank. And so if you want 10 times more energy, you just need a 10 times bigger tank in terms of its volume, and tanks are cheap. Whereas for a conventional battery like a lithium ion, you need literally 10 times more batteries, so it costs 10 times as much. So that's the idea. And vanadium flow batteries have been around for a while. Vanadium flow batteries are well known. But vanadium is expensive. It has price volatility, and it would be nice to find something much cheaper. So our concept here is to replace vanadium on the one side with a manganese couple. Manganese is extremely abundant. This electrolyte is only 1/10 the cost of a vanadium electrolyte. And on the other side, where the vanadium reaction is rather slow, to use a closed circuit hydrogen loop in which we either make hydrogen and store it, or we use hydrogen effectively in discharge mode, a bit like a fuel cell. The other advantage of this is in the fullness of time, if hydrogen economies come through, we can also couple this directly into a hydrogen loop. We don't even need a hydrogen store, and we get a very high efficiency, effectively reversible fuel cell electrolyzer. If we make hydrogen in an electrolyzer at say 60% efficiency, and we convert it in a fuel cell at 60%, we're about 36% round trip efficiency. This is an 80% round trip efficiency. So that's the idea, and that's the innovation. And we have some core patents on the concept of liquid gas flow batteries, both in acidic and alkaline chemistry. And we're pursuing that through a spin-out company that we've set up called RFC Power, which has now got 6 employees and is based in Imperial College's own entrepreneurship hub, essentially, in one of our campuses. So this is the chemistry. On the cathode side, this reversible manganese couple. On the anode side, a reversible hydrogen couple. Overall, we get 1.49 volts, open circuit. This is only possible because we've addressed this disproportionation reaction. It's normally regarded you can't use manganese because it does disproportionate and form a precipitate of manganese dioxide. But some excellent work by my colleague Anthony Kusanak in the chemistry department has found a way to stabilize that reaction with some titanium additives. So that has enabled us to go down this route. This is a paper we produced on this work, showing that we can get very high power densities, at least in a university laboratory. Harder to achieve, of course, in a technological device, but shows the prospect. And this is some work from RFC Power, and you probably can't read this because it's not very clear, but that says 700 cycles. So this is just some preliminary testing, and now we're well into the thousands, showing that the device has long-term stability, which is what you would expect for a flow battery. They should be capable of cycling tens of thousands of times, unlike a lithium-ion battery. So we're excited by this. We've received seed investment, and the company is taking the technology forward. Finally, just want to talk about the role of hydrogen in terms of providing long-term storage. As I say, in Northern Europe, we're likely to go down a primarily wind power route. The challenge is that also in Northern Europe, around this time of year in our winter, we often get a period of low wind. And that period of low wind can be several weeks long. And obviously, if we've built an energy system reliant on wind power, and then we have a period of low wind, we need to find a way of backing that up. And backing that up with natural gas is obviously not a low carbon solution. So the question is, can we back it up with hydrogen instead of natural gas? And this is some calculations that look at a future UK energy system with high wind reliance. And if we had, say, a period of 3 or 4 weeks of low wind, we would need something in the order of 30 terawatt hours of energy storage to back that up. Now, this is the UK's only pumped hydro facility. It's in Wales, in the west of the UK, and it's this is the upper lake, and there's a lower lake. It's a 9.1 gigawatt hour energy store. We need 3,600 of these to provide that level of backup. We do not have 3,600 places to put it, let alone the cost of building it. 1 million tons of hydrogen would give us the same capacity as 33 terawatt hours if it was stored underground. Can we store 1 million tons of hydrogen? Well, there's been some really good work by this group in Germany who've produced a nice paper, very nice paper looking at the capacity for long-term energy storage in Europe, in which you use solution mined salt caverns to store that hydrogen. We do that currently for natural gas. We store 10,000 gigawatt hours of natural gas in the UK in underground solution mined salt caverns. And there's more than enough capacity to support the whole of Europe, although of course it's not uniformly distributed. But nonetheless, there certainly could be enough strategic energy storage if that's what we chose to use hydrogen for. And then finally, my last slide is to remind us that actually it's not only about residential and transport, it's also about industry. And I think the role of hydrogen to support decarbonisation of things like the steel industry, to move away from carbon-based blast furnaces. We simply can't continue to produce steel using carbon as our reducing agent. If we do that, half the world's entire carbon budget will be used by the steel industry alone by 2050. So that's not an option. But you can use direct reduction of iron, in which you use a reducing gas to reduce iron oxide to iron. That's done already using methane as the reducing agent. And it's very, it's not a big stretch to think about using hot hydrogen of the high temperature electrolyzer as the reducing agent for that process, together with the opportunities for steam integration that would improve the efficiency. Same with ammonia, really big opportunities to think about how we make green hydrogen and then green ammonia. And there are big global programs to try and then think how we might move that ammonia around the world. Okay, so my last slide to give us some time for some questions. I hope what I've shown you is that electrochemical technologies have an important role to play. They've not received the global attention you might have hoped for many years. So that gives us opportunities for innovation and need for innovation. All of these technologies are underpinned by materials science and materials engineering. And they are devices, so you have to be able to manufacture a device, so the integration of materials matters. As I've highlighted some of the areas of focus and application, and we think we're doing some great work in the UK in this place, but I just want to stress that we have to collaborate internationally if we're going to develop and deploy these technologies at the scale and speed that the world needs. So it's a great opportunity to talk to you today. There are a bunch of links here if you'd like to pick up on any of the things I've talked about, our work at Imperial, the broader work in the UK Hydrogen and Fuel Cell Supergen, our work in the Sustainable Gas Institute and our Energy Futures Lab. So I'll leave it there and open up for questions. Thanks.
Thank you very much. Thank you very much, Professor Brandon. Yeah, so your talk contains a overview of the current technology for low carbon technology, fuel cells, and also your own important contribution to this area. So now I would like to invite the audience to come forward with questions. You can either speak up, unmute yourself, or you can type a question into the chat box. Yeah, please.
Shall I stop sharing? Would that be easier? Or shall I? I'll stop sharing. Right.
So any questions? Yeah.
Okay, good. Thanks. Okay, thank you. Thank you very much, Nigel. It's great to hear from you, particularly on the recent developments. And one of key point is the new spin-out flow batteries. I remember the hydrogen cell concept was proposed only a few years ago when we started the low carbon energy storage consortium. So it's nice to see another excellent example of turning science technology into practical applications, which is very important nowadays when we're looking at increasing pressure of climate change at a really alarming scale. My questions are a few actually, maybe related to some of the key points you mentioned during the talk. The first one is particular to regarding the large variations of natural gas demand at different time of the day or different time of the year, the seasonal demand. I understand that there's a trend in blending hydrogen into the natural gas in order to further reduce, if you like, the carbon content in gas. And this is something which actually been strongly considered here, even in Hong Kong as well. I wonder whether you could comment on that kind of potential, maybe as a first question. Yeah. Okay. I'll ask more later.
Yeah, sure. Okay. Well, look, I think that you can certainly put hydrogen into natural gas. You can certainly put it to a certain point. Once it goes above about 6 or 8%, I can't quite remember the number, but it's not a large number. The combustion of the natural gas is impacted, and then that affects the end use of the natural gas. So you can put in some hydrogen. I mean, that is helpful. It lowers the carbon intensity, but it is not a solution to the carbon challenge. What it really is it provides a market, an early market for those people producing hydrogen to sell that hydrogen and to have a way of transporting it and using it in a way that's useful. So I think for me, it's a mechanism to bootstrap up the hydrogen generation side. It is not a solution to the carbon intensity of natural gas, because you can't put enough hydrogen in you can't certainly get to net zero, right? You can lower the carbon intensity by 10% perhaps, but you can't go to where you need to be. So it's a useful market mechanism for providing a retail opportunity for early markets for hydrogen, not a solution to climate change.
Okay, maybe I'll continue to ask the second one. It's related with all the electrochemical devices we've been working on, whether the high temperature, low temperature. Now, the key point to get blue or even green hydrogen is the renewable electricity, that our electricity with carbon capture that we have to probably have to sort of implement quickly. But given they are increasing sort of efficiencies in PV in the last decade, from 10 to 20%. But if you look at the total demands on the power, the electricity demands required to generate green or blue hydrogen, that's still enormous. The current implementation of this PV, even in China, is we're talking about tens of gigawatts per year, but still that's not enough.
Yep.
Given the strong pressure on the one hand, the green electricity is not forthcoming quick enough. How would you think of better ways, more economic ways forward to get our path practically right towards 1.65 degree?
Yeah, look, I mean, there is a transitioning the world's energy system to renewables is not an easy task, and you're absolutely right that there's a supply chain issue in there. In other words, how can you manufacture the product fast enough? Certainly, and the same happens with wind. So in some parts of the world, it'll be solar dominated. In other parts of the world, it'll be wind dominated. In both cases, you need to think about your supply chain, and of course, it's not just the build of the kit; it's the installation of the kit. And how do you? Classically here, where we're going for offshore wind, we do not have a port big enough to take the ships that will be needed to install the new large wind turbines. So we're going to have to build new ports to take the ships, to take the turbines to install them. That's happening, and billions of dollars are being put to work to make that happen. But I think the point you make is valid for things like carbon capture and storage. So making hydrogen from CCS, whilst it's not as low carbon as making it from renewables, it's still a lot better than making it without abatement. And I do think there's a role for technologies like that, because they can be brought to scale really quickly. We know, thermochemical routes to hydrogen are scalable and lend themselves to. So I think for some large industrial applications where we might want to get going really quick, then there's a role for that sort of technology to bootstrap it up. And we also have to recognize that the whole thing's not going to happen overnight, right? It is going to be a 20, 30, 40-year journey. Whether we can really keep everything to 1.5 degrees, I think, is a really challenging ambition. But what we certainly shouldn't do is not try, because otherwise we really are in a mess. So I think that we're doing the right things. You go as quickly as you sensibly can. But you're right, it's a hell of a challenge, right? And but therein lies some great opportunities for companies and organizations to transition into whole new business models and business enterprises. Yeah, so I'm not to underestimate the scale of the challenge. It's enormous, and it's one of the reasons I get a bit frustrated sometimes about kind of arguments between different parts of the hydrogen community saying it's got to be blue, it's got to be green. Actually, it just needs to be hydrogen, right? I don't really mind. We need everything.
Good, thanks. I'll give it to other colleagues.
Okay. So Nigel, so there are a few questions from the audience. So just read it out. So the first question is...
I've got them, I can see them. So
you can see, okay, you can directly answer the question.
Yeah, so kind of hydrogen generation produces a refrigerant for chiller systems. So I think what that refers to, I guess that's the question around the endothermic nature of electrolysis. And the answer is I don't think that is going to work quite in that way, if I'm understanding the question correctly. You would cool the incoming gas stream. You need to be at temperature, and you would cool that gas stream down, but I don't think it would act as a refrigerant, unless I've misunderstood the question, in which case please put a clarification in. And then a question around safety. And heat dissipation. Yeah, I mean, it's a very valid question. So the first thing to say, these high temperature systems are hot on the inside, but they're not hot on the outside. They have, you can get really high quality thermal insulation, which will keep something at 800 C in the middle, and it's just sort of safe to touch on the outside without layers and layers of of thermal insulation these days. So heat dissipation, the device developers don't want to lose heat because heat's valuable, so they go to a lot of care and trouble to make certain they're not, and they're perfectly safe to touch, so they don't get too hot. They're hot on the inside, but not hot on the outside. So I think it's fine. Valid question, but there's a solution.
Okay. So any other questions? Yes, Vivian, please.
Vivian's waving.
Yeah, so since there are students also listening to the talk, and as I mentioned at the early part in the introduction, the Hong Kong government as well as the university is now try to invest quite a bit for entrepreneurship and sort of to motivate the young people. So I was wondering, in your spinning off of your companies while you're at Imperial, then how much involvement were your graduate students, or are there undergraduate students also involved in this sort of spinning off experience?
Yeah. Okay, so I think I'll answer that in two ways. So first, so I'm head of engineering at Imperial. So I think one of the things I'd say is that we've been really keen and continue to be really keen to give our students the opportunity to have an entrepreneurial experience if they want. It's not mandatory. And I think we need to be careful to not make it mandatory because it's not for everyone. But it is for those students who want it, something that we try and provide. We have training programs for those students that wish to go on it. We have the largest hack space in Europe at the university, and I think giving students and staff this chance to just go and build stuff is really important. So providing those kind of physical embodiments and physical environments where students can get together and go and do stuff is an important piece. We're spinning quite a lot of companies out from that have been developed by students. We provide a lot. We have an informal, free-to-use service of advisors. These are people that are often retired industry people or people who've done venture capital who just want to kind of give something back to the community and feel that they can help and do help, you know, giving student wise advice. We do the same for staff as well, because there's a duty of care here. Going commercial with your technology has risk. It has financial risk. It has personal warranty risk. It is not free of risk. So making certain that people are aware of the risks that they're taking on is important. We have again a space in our new campus in West London where we provide opportunities for companies to start up and so on. So it's around support for staff and support for students. In terms of these specific companies, then it was really the graduates, the postgraduate students that were, so it's the PhD students and the research staff. In the case of the flow battery company, that was co-founded with 2 postdocs. In fact, one of those postdocs founded this and was involved in another company and chose to go and run that other company. And the other postdoc was involved in this and then went and founded another company, which has just raised a very large amount of money. That's a lithium battery company, but he's still a director of the business. In the Ceres Power case, we hired quite a lot of, there's quite a lot of that company have come from Imperial College. Not all, because over time you've expanded your recruitment base to include colleagues from industry and so on. So it's a pathway for people to get employment, jobs, all sorts of exciting things. Sometimes they've been directly involved in the innovation. Sometimes they have not, but there are still job opportunities or you know, opportunities to join innovative small businesses, which are, you know, exciting for some people if that's what they'd like to do. And as I say, as an institution, we're doing a lot to try and help encourage the entrepreneurial journey. You know, if you're going to take a risk early in your career, right? You haven't got a lot to lose, and you learn stuff. So it's a good thing for people to do. Yeah, I'm just seeing a question in the chat as well around water vapor and its global warming potential. So it's a good question around the GWP of water vapor in the atmosphere. It does have an impact. I still think it's a rather open question. You know, methane has a global warming potential of about 80. The data I've seen for hydrogen is about 5. So, you know, we don't want to lose hydrogen and we need to manage it. But it's nowhere near as bad as some of the other gases. That's not to say we shouldn't be complacent about it. And then the ammonia approach. Okay. So the advantage of making hydrogen into ammonia is that we know how to move ammonia around the world at scale much more easily than we can move hydrogen. However, it's an efficiency, and you pay an efficiency penalty and you pay a cost penalty for making it into ammonia. So you should only do that if you can't move it as hydrogen, and you should only make hydrogen if you can't move it as electrons. So assuming it's coming from renewable power. So you also have to have these things in mind. So I don't think the ammonia approach is a temporary solution. I think if you're going to make ammonia in the middle of the desert, if you're going to make hydrogen in the middle of the desert in Australia, how are you going to get it to your market in Japan? And I'm not certain that making it into liquid hydrogen and moving it at that temperature in a vessel is practical. So making it into ammonia is perhaps a sensible option. And you can run a ship on ammonia quite well. Diesel engines can be converted to run on ammonia at quite high efficiency. Sorry, Vivian, I just answered the questions. Did I answer your question?
Yeah, sure. Yeah, it's very helpful for our students and also for us, I mean, to how to plan to help the students. Yeah, thanks a lot.
Yeah, and we can follow up by all means if you'd like to. I mean, I'm not an expert on how we do the education of entrepreneurship, but I have many colleagues who are dedicated to that.
Yeah, we would love to seek your advice and those from your colleagues. Thanks a lot.
Right. Good.
Yeah, okay, so I think that's the end of this session. Yeah, thank you very much, Nigel. I hope, when the pandemic is finished, we will have the opportunity to invite you over to, can have more close interaction, and then you possibly, as you mentioned, international collaboration will be very important for the growth of this field. Hopefully, you can have some close collaboration with our colleagues working in the similar area. Thank you very much.
That's great. Okay, look, thanks for your attention and invitation. Have a good day.
Thank you very much. Yeah.
Thank you.
Yeah, see you. Bye-bye.
Back again.